Okay, so we're back in business, and so I'm talking about. Okay, so the questions have come up. I talked about this in a backwards way. I said, well, suppose we started with the ground state and we wanted to chop it into it and compress it, but of course you can never do that because you know on a big system you could never represent it. So what you have to do is you make use of this thing that I described to say, yes, there exists a matrix product state that is close to the ground state. And then you write down a bad one that has that size, and then you try to improve it to get to the ground state, okay? But you never, you know, it's never practical except for like 12 or 20 site systems to actually form it and then do the SVDs like I showed. Okay, so finding the ground state is sort of the crucial part. And so I'm discussing what strategies you would have. So we have the form of the compressed wave function as a matrix product state, and it's bad because we just put in a bad guess or something. We want to optimize all these coefficients. Okay, so I said that the machine learning approach will not be very good. Imaginary time evolution is okay. And so let me explain about that, because that also allows us to do other things like dynamics, right? And it's something that you probably have heard a lot about or worked with. The Trotter decomposition is one of the key ways. Okay, so how do we do a Trotter type decomposition for imaginary time? Okay, and so the first one to do this Trotter type decomposition in the context of matrix product states was Vidal. He called it time evolving block decimation, and he did not know what DMRG was at that point, so that was the sort of a point where the quantum information fields started merging with the condensed matter simulation fields in DMRG. So, but it turns out that he sort of reinvented something that was almost DMRG. And then there's another version of it which just does in the DMRG language called TDMRG. Okay, but so the idea is that we have a Trotter breakup, and so let me write it like this. So I have a small Trotter time step h, and I'm going to do the even odd breakup. So I separate out the odd bonds and the even bonds, and then I make gates out of them. So this will look something like this. There's two layers that are sort of interleaved, and one is the odd bonds and one is the even bonds, right? Have you all seen this sort of explanation of the Trotter? It's like these are the, if you're doing a quantum computer simulation just directly working with the qubits, you can form these gates, and you would put an I here to make it unitary, and then you could form these gates, and you would apply them in this fashion because this is an accurate representation of the time evolution for a short time. Okay, so how do we do this for an MPS? We just think of writing an MPS down here. Okay, and then we think of applying these gates one by one. Okay, so we're going to have a matrix product state like this, and I'm going to apply a gate, say, at this piece, somewhere in the middle of the calculation. Okay, so the gate is just, a 4 by 4 matrix. So the gate is something I know, it's easy. So what do I do if I have a matrix product state? The first thing you want to do is you put the orthogonality center on one of these two sites, right? So we choose our gauge, we can move the orthogonality center around, we put it here, and that makes every thing that you're doing sort of behave nicely. We apply the gates, so that's a contraction of the gate with these two objects, two tensors, okay? And so we contract it together so it looks like one 4-index guy. And then we split that with an SVD. Okay, so there's an SVD that does that. Now, The SVD here is very much like when I was doing an SVD of the whole wave function. Okay, but there's a mistake you can make, which is if the orthogonality center isn't on one of these two sites, the error in the SVD could be much larger than the error you get for the whole wave function. The singular values don't really mean what you think they mean. So if you put the orthogonality center on one of those two sites, the SVD will be faithful to the best truncation of the wave function that you can do with that SVD, even though the SVD is only on this little set of, it's splitting one tensor into two that's very small. So this, taking an object with these four indices and splitting it with the SVD is sort of a universally, almost all the algorithms will do something like that, including DMRG. It's just how did you get the piece that you had before you split it with the SVD? So in this case, it just came from applying one gate, okay? And when we split it back together, we end up with a matrix Pottix state again, okay? So then we can apply the next gate, okay? So we would apply this gate, okay? Put it together, split it apart, move the orthogonality center here, apply that gate, split it apart, move over, and we would sweep from left to right and apply one row of gates, okay? Then we go back, our orthogonality center is over here, so we start going backwards and we apply it the other way to the next row of gates, okay? So this turns out to be a very easy algorithm to think about, to organize. The only ingredients are applying a gate and doing the SVD and moving the orthogonality center, which it can be sort of almost automatic for this. Okay, so this sort of algorithm is something that you can, if you were sort of just learning this and writing code on your own without too much help, this would be a place you could start very early. Okay, now because we're not on a quantum computer, we're not restricted to unitary gates, so this can be a non-unitary imaginary time gate, and what that means is that it will just take us straight to the ground state without all the difficulties of finding ground states from quantum computers. So that's nice. Drawback of it is that you have to apply these gates a whole lot of times because the tau is controlled by the accuracy that you want and the size of the terms in the Hamiltonian. So it's sort of like a tiny time step. And how far you have to apply it depends on the lowest energy gap. You have to resolve the ground state. And so it's like that ratio of the sort of larger eigenvalues of the Hamiltonian to the smaller energy difference means a lot of steps. And so this is not nearly as efficient as DMRG, but this is a nice method, okay? And importantly, you can just use it for dynamics, okay? But dynamics is hard for a tensor network, so how does it get hard, right? Well, what happens if so this is a little side note before we get to DMRG, okay? But so why does real-time evolution fail? Okay, and the answer is the entanglement grows. Okay, now, if you were doing real-time evolution of the ground state, well, it just stay the ground state. So that's not what we're talking about. So we have to think about how are we different from the ground state. Okay, so if we think about one of the things that we often want to do for practical reasons is we take the ground state, which we found in some way, and then we want to flip one spin. And this mimics an experiment like photoemission where a photon has come in and flipped the spin. And so it's like, oh, we flipped that spin. That one local change does a lot of change to the whole energy spectrum structure of that state. It's no longer close to the ground state. It's a mixture of excited states, and that's what we want to understand in some experiments. Okay, so we've essentially applied like S plus on one side. Okay, so what happens to the entanglement when you do this? The first application, you apply the S plus and it only affects one tensor. So it does nothing to your entanglement. It's just, changing the values of one of the matrices, none of the bonds. But then you time evolve it in real time. Okay, and so it's like you have this higher energy piece of it, and this starts spreading out. Okay, and it spreads out its energy, because it has an extra energy, and it spreads out entanglement. It's like you could think of it like, oh, it's like shooting out particles in both directions, and those particles are entangled. And so it tends to have an entanglement growth that looks sort of like a light cone, like that, and this is the position, and as it grows, the entanglement spreads out. So, so the entanglement tends to grow in these, but I've done a lot of calculations like this with the MRG, and it was the best way to do those calculations because the entanglement doesn't grow so fast. So in a Heisenberg model, we could often carry out these calculations to a time, if J is 1, we could carry it out to a time of 20 or 30 before the calculation got too big for the computer. So what happens is that you monitor the calculation and you monitor the SVD and you make sure you keep enough singular values so that you're not making a big error. And then the matrices grow. And eventually you run out of memory or time and you sort of stop. So that's one example of entanglement growth. That's one of the things that goes wrong. And then this is not the worst case because when you just flip one site, it's just a small, the energy associated with one site and it kind of spreads out to a smaller energy over a larger region. Okay, and so the worst sort of case you could do is if you start out where something is universally not the ground state, but to even write it down, we need it to be a low entangled state. So suppose the ground state was, suppose the model was an antiferromagnetic Heisenberg model where it's like mostly up, down, up, down. I could do something like up, up, down, down, up, up, down, down. And this would be something where I could start with this state, and it's actually a very high energy state because every other bond is kind of broken. And so this would be a pretty high energy, but I could start it out as a perfect product state, bond dimension 1, and then evolve it in time, and this goes bad really fast. The matrices just go very fast. All the entanglement is sort of spreading out from everywhere. And so, people understand sort of how that works. There's theories about it, which, I haven't worked on, but this is pretty well understood. So lots of reasons why dynamics can cause entanglement growth, and what we're talking about is not going to work. Okay. The other, and it sort of looked like a rosy picture so far. So let me point out the other case where things are not going to work, which is higher dimensions. So I've been drawing spin chains like that's the only system in the world. And so the question is, what happens if I have, say, a 2D system? Okay, and the calculation is still going to be controlled by the SVD where I split a system in two. So I can draw a line like this and consider the entanglement when I cut a system like this. And so if we go back to my picture of these little valence bonds as my cartoon of how this works, I can draw valence bonds, but every once in a while I'm going to draw one across the boundary, right? And so the number of bonds that you're going to cut is basically proportional to the area of the cut. And this is called, so this is S is proportional to the area of the cut, and this is called the area law. And it's something that people have worked hard to prove in the cases that they could get a handle on, 1D cases especially, something that you'd like to prove. It's known that, the area law has log corrections in cases with a gapless ground state. And so certain things are known. But regardless, 2 dimensions has this entanglement that grows proportional to the width. And that entanglement, the bond dimension essentially goes as the exponential of that entanglement. So there's like m goes as e to the s. And so it gets exponentially hard in the width. So when I show you these DMRG calculations that are like, I'll show you some that are really accurate. Okay, so you can do them on finite strips by treating the strip as a 1D system. Okay, so I can just map a 2D system as a strip onto a 1D system with some long-range interactions. Okay, I can put those at long-range interactions into my MPO, that's not a problem. But there's no hiding the fact that the entanglement entropy is big, your matrices are going to be much bigger, it's going to be a much harder calculation. Okay, so when we do DMRG calculations, the question is, how big a system can we do? And so the answer is about L by 12 for frustrated spins. Now, and usually we make this 12 in a cylinder. So if you chop a cylinder in 2, it's the same as chopping a strip. The entropy is about the same. Width 12 is pretty good. So there's a lot of frustrated spin systems that we can solve with DMRG and do a nice job. If you look at an electron system with doped electrons, like the Hubbard model, there's L by 6 is about the limit. And this is not satisfactory to solve high TC, right? So this is, DMRG doesn't, solve high TC on its own, but for many of these frustrated spin systems of practical experimental work, we sort of trust the phase diagrams out of DMRG. Okay, so that's jumping a little bit to what this can do. Okay, so how do we actually do the DMRG to find the ground state that's better than the imaginary time evolution? Okay, so the key thing about the Trotter gates is that they're only working with the Hamiltonian a little, yes? Yeah. Oh, do you have the box?
So I'm a bit confused about what 12 represents.
Yes. So I'm just thinking of a square lattice Heisenberg. Sites.
Okay, so L is one dimension and 12 is the other dimension.
Yeah, so it's usually links and, it depends on lots of details about the system. But, it's not unit cells because, it doesn't care about whether it's a unit cell. It cares sort of by the number of sites across.
Okay, and while I have the box, I was wondering, what's your opinion on neural quantum states?
On what?
On neural quantum states.
What quantum states?
Neural quantum states. Like you represent your wave function as a neural network, because you said that gradient descent is not really good for ground state calculations, but it seems that neural quantum states.
What kind of quantum states? I don't
neural quantum states.
Neural network states?
Yes. They seem to be quite successful nowadays.
Okay, so neural networks is a alternative to represent states, which doesn't have the same weaknesses as DMRG. It has other weaknesses. That's great. None of our classical methods solve everything. So neural network states don't have this dependence on the transverse direction, but they don't have as good an optimization as DMRG. They're a little bit harder to work with, but that's an area under active investigation. Yeah, there's a lot of competing methods out there, and my approach is, there's a lot of, condensed matter problems that I'd like to solve, and chemistry sorts of things that I'd like to develop methods, and it's sort of a question of can we attack some of those systems with an effective method, and so for some of them, some of the other methods are much better. Some of the quantum Monte Carlo methods can be very effective for the larger systems. No, there's no universal method. Okay, so let's see. So how does then DMRG work? So when I do time evolution, I'm sort of optimizing one gate at a time, and it doesn't know about the rest of the system. So DMRG uses this MPO, or the whole of Hamiltonian, and so we work with usually two tensors, somewhere in the middle. That's our basic unit. And we think of this as a psi effective. Now, it's just a little piece of the wave function in some sense, but these external links actually point to all the sites outside. So what it actually is it's just sort of a reduced basis representation, a truncated space representation of everybody else. And then the two sites in the middle, if we think of that, they don't have any truncation. We can do whatever we want with those. So this is sort of like a subspace method, truncated basis method, different words for it. We think of this psi as psi effective, and then we're going to do exact diagonalization on it, using the techniques of exact diagonalization, which have been nicely developed. And one of the key tools is the Langshos algorithm for iterative optimization of the ground state of a matrix. And the Langshos algorithm is rather well behaved. It's rather nice, and a lot better than gradient descent. So what we're going to do is we're going to do a little ED on two sites. Now, to make this sort of a faithful representation of the whole system, one of these two sites has to be the orthogonality center. Okay, that's just all the pieces sort of fit for that. And we have to write down the effective Hamiltonian. And the effective, remember I had the MPO look like this, and I had sandwiches of it, right? That was the whole contraction. So H effective is this guy with, okay, so that's the diagram for the H effective corresponding to these two bonds. Now, you can see that it fits in the right way because what you do with an effective Hamiltonian is you multiply it by a vector with the shape that fits. So these four links is exactly where I can fit my wave function in. Okay, and then it has four indices out, and that's the output. So it's like saying C equals H effective phi as part of my iterative solver equation. Okay, oops. Now, these edge tensors here, so that's the contraction of half of this thing. So it's like erase one half. So it has all the information about the entire left-hand side of the system and its whole Hamiltonian, okay? And so it's putting the whole Hamiltonian, the left side into that part, the right side into this part. And so the key thing is that if I work with the effective Hamiltonian, and I have E equals psi H psi, that's equal to psi effective, H effective, psi effective. So I'm working with just a little piece, but it's like I'm working with the whole thing. The energies that I get out are, if I take that MPS and expand it out and do the whole sandwich, I will find that I got the same energy as what I just got out of the little piece. So again, it's like the evaluation of an operator just with the lines around it gave the same thing. This is the version where you have Hamiltonian pieces going all the way out. Okay, and so we do Langshos, or one of its cousins, which is sort of the version of ED. Okay, and we find a better psi effective, and it's guaranteed to lower the overall energy because, you know, we just optimize something that's a faithful representation of the total energy. So any improvements that we make translate to the improvements in the whole wave function. Okay, once we do that, so we get a good psi effective, okay, at that point it will look like this thing. It will not look like the two tensors that you started with. It'll look like a four index guy, and we do our SVD. And it turns it back into two tensors of a matrix product state. Okay, and then I can sweep. I can move to the next site and re-optimize. Okay, so there's a sweeping process that just goes back and forth, sweeps. Okay, at every stage you lower the energy. At every stage you find sort of the best energy with the knowledge that the system has about, you know, what the rest of the system is doing. There's no overshooting. There's no, you know, when you do trotter, if you make your tau too big, you can kind of overshoot and get a bad energy. And there's none of that. It just finds the sort of best thing. Okay, so that's the sort of, so that aspect of it working so well because it borrows some of the nice things from exact diagonalization and this framework is sort of the reason why DMRG is, or one of the key reasons why DMRG is so effective. The other one is that for 1D systems, matrix product states work well. Okay, so let me, I want to show slides again. Okay, I wanted to show you how easy it is to use iTensor to do a DMRG calculation on a spin chain, and to do it flexibly so that no matter, you know, you can put a whole range of Hamiltonians in there and you know, this is the whole code. Okay, so this is in, is there a laser pointer? Okay, good. That works. Okay, so this is a whole DMRG code, and so first of all, iTensor is written in Julia, so I think you can see as you look at this that okay, it's like you know, lots of other computer languages. There's only a few things you sort of need to learn to know how to work with it. So at the top, we say using iTensors and iTensor MPS. Okay, so that calls it in. You know, the downloading of iTensor and iTensor MPS is just a one-line thing. When you get Julia by clicking on Give me the package. And you drag the Julia into your applications folder. And then you type it, Julia, on the command line. And then you say add iTensors, add iTensor MPS, and it goes and gets it from the internet and puts it in a secret place. And so you just don't have to, it's like, you don't have to think about it. Okay, so what is going on with this program? Okay, so we're gonna do a 100-site system. Okay, so the first thing we need to do is define the indices for the sites, and that tells us what kind of system we have. Okay, so we're saying we have a spin-1 system with 100 sites. And you need to work with these site indices. Okay, so a lot of iTensor is all about working with the indices and then also the tensors. Okay, and then this is where we build in the Hamiltonian. Okay, so it's a sum of operators. I talked about the Hamiltonian as being a sum of all these terms. So it's written so that you can just write any old Hamiltonian you want. with this notation. So this sort of common notation was sort of something that worked very well with Julia's syntax, okay? And so, you put the coefficient, the name of the operator, which site it's on. So there's a for loop around this, and we're doing all the bonds, and we're not connecting the last bond around, so it just goes from 1 to n minus 1, there's the loop. And then we do our s plus, s minus on near neighbors, and s minus, s plus, and do the sz term. And this is implicitly assuming j is equal to 1. And so you can enter all sorts of Hamiltonians like that. If you want to put an extra magnetic field on one site, okay, you just, before you create the Hamiltonian, you just put an extra line, add in this term with only an sz on it on one site, okay? So that's all you need to do. Okay, then the next part is controlling the DMRG. So we say we're going to do 5 sweeps. So we're going to go back and forth. The sweep is back and forth. Okay, we're going to do it 5 times. This tells how big we want the matrices at each step. Okay, so we're going to start out by 10 by 10 matrices. Now that's not very accurate, but our guess is pretty bad. So that's big enough to go fast and make an improvement. So gradually we ramp up the size of the matrices, and it gets closer to the ground state, and then it can get closer because the matrices get bigger, right? So it's very efficient. Okay, we tell what sort of cutoff we want in the singular value decomposition. Okay, then we tell it a random starting state. So this will say that we're going to use bond dimension 2 to make a random state as an initial guess. Okay, and you can put in other things, but, and then you just feed that into DMRG, and it uses that stuff, and, it will spit out the energy in, a minute or something. So that's, it's really very easy to use, and this opsum thing for making Hamiltonians is really a sort of nice tool. If you want to, so of course in practice you're going to measure properties, and but it's all described on the iTensor website. When you want to do a calculation of, say, the energy gap, for a spin system, there'll be an energy gap that has to do with a different angular momentum overall. So this system is not paying attention to angular momentum conservation. The random state will be sort of a mixture of different values of total S sub z. And so you can turn on angular momentum conservation with just essentially sort of one line. So this is with conserved angular momentum. So when you define the indices, you say conserved QNs equals true. Okay. Now what's involved in that is, so we know that Hamiltonians are block diagonal by angular momentum. It's like there's a certain, total S sub z sector, and that's a block on the diagonal, and then there's another one and another one for each value. And we can think of those as having ground states in the different sectors. So, and when you apply the Hamiltonian, because it commutes with this operator, you stay in the sort of the same block. So we can start our DMRG in the block that we want, and it will stay there. And so to do that, you have to choose, so this part is the same, and then this part, we're gonna choose the sector by saying there's an equal number of ups and downs, and we're gonna try to choose a good guess by making it the up-down pattern. So you make it an up-down pattern, it'll automatically be in the SZ equals 0 sector. You start with that state, and we have a slightly different thing. We make our matrix product state without the random word here. And so this is a product state. And so you can start with a product state and then do the same thing, and this will just work. Okay? Questions?
So you were saying with geometry can compute also the ground state is some single sectors.
Yeah, so if I flip a spin, so these are just strings, right? So, notice this bracket here. So this is how you create a vector on the fly. A lot of times you might like initialize a vector and then fill it with a for loop. But this is just a shorthand that does it on the fly. It creates this vector n long and puts these strings in it, and this question mark is a little bit of, syntax. It's like an if statement that's borrowed from the C language. But, so there's a little bit of Julia trickeries, which you've probably seen in other languages. But I can just put in whatever spins I want. And if I take one of those downs and make it up, then I'm going to get an excited state, right? And that will be great to do. Then you can choose to get these two ground states with different sectors, and you can subtract them and get the energy gap. Okay? And you can work your way up to the different sectors. And question?
So you mentioned the sweeps like going back and forth and back and forth and back. Like, why is that necessary if it's just contracting tensors?
So what it's doing is it's optimizing the tensors two at a time. And the first thing that you might think in making this algorithm is to optimize one at a time, because why do more than one? And then you could, so the idea, this is an idea that, well, when I developed it, I just thought, well, this is a weird thing. Nobody's going to understand this. Why am I doing it one piece at a time? And, but now there's something called alternating least squares, in math. And I think it is probably, I just didn't know about it. But it's like minimize a little piece at a time. That's a nice way to do minimization. It's like you're not as likely to get stuck in flat spots in the gradients, that sort of thing. So you take a little piece of the problem and you optimize it. The smallest you could do would be just optimize one site. And that has some drawbacks.
I guess my question was why do you go back and forth instead of like
well, you're doing an
go in one
optimization, and so it all has to know about what everything else is doing. It's all interdependent. There is entanglement all the way, or correlations all the way across the system. So if the left-hand side of the system is like doing something, that feeds all the way to the right, okay? And so you have to sweep back and forth to transmit the information that's encoded. They're all the tensors are sort of linked through minimizing the energy.
I see. Thank you so much.
Okay, let's see. Here is one little slide just to show how well it works. This is from 1993, and it was when the spin-one chain was, still a controversial topic about whether it had a gap. And here we worked really hard to get the ground state energy of the infinite system. So trying to go to systems large enough where we could, and we got all these digits. And then this is showing the convergence of the spin-one half chain. So the top system has this gap. It's called the Haldane gap. And this one doesn't. But there is a gap just to a finite size. So in this case, this is the size of the gap, or this is the first excited state, which it's a 2,000 site system. And so if the system went to infinity, the gap would go to 0, but this is what it is. It's like 1 over 2,000 roughly. And so the convergence in DMRG sort of just goes past that, and then it sort of straightens out to look sort of exponential here. So it's like now it knows it has a gap, and so it tends to converge somewhat exponentially once you're past that. Okay, so for these 1D systems, you can just, this sort of problem you can do on your laptop pretty easily. And I think that's all I wanted to show. This just shows a little bit of the time evolution. Okay, so let's see. I think that's basically what I wanted to cover. So I'll take any more questions. Yeah.
Just a basic question. So what does this have to do with renormalization in general?
Very good question. Okay, so So one of my thesis advisors was Ken Wilson, who developed the renormalization group. And he developed a method called the numerical renormalization group, which is still used. And with that, he solved the Kondo impurity problem. And it was essentially using matrix product states in sort of a hidden way. And so this numerical renormalization group, it was more organized like a renormalization group where you sort of get rid of high energies first and then work your way down. Then people said, this works so great for this impurity problem, let's try it for other things like the Hubbard model, and it just failed. So my starting point for this was to fix the numerical renormalization group. Okay, and the solution to fixing it was to essentially think about the SVD Schmidt decomposition, which is another way of talking about that is, the reduced density matrix, another equivalent. So I sort of through a long route, I figured out this insight about that, and then I didn't call it the SVD renormalization group because reduced density matrices, that's like a cool thing in Feynman's lectures on StatMech. I thought, oh, everybody will like that. And nobody knew about the SVD back then or the Schmidt decomposition. So it's like I described it in terms of that. But it was all historical. And the renormalization group itself is kind of a weird name to start with because it's like not a group, it's a semi-group, and it's kind of, it's kind of a weird sort of history. So it's perfectly okay if you just say DMRG and don't expand it out.
Inside the whiteboard, you wrote down that energy is, which is psi, Hamiltonian psi is equal to psi effective, H effective, and psi effective. Actually, I don't see how is it true. So is there any very special gauge fixing also happening for the Hamiltonian as well?
So if you just take what the definition of the edge tensors and expand it out, you'll see it all makes a sandwich.
Oh, I mean, for state-wise, I completely understood, hopefully, but here's additional nodes are there for coming from the Hamiltonian. So Hamiltonian is also gauge fixed so that construction is very simplified.
The Hamiltonian is inserted sort of in full. That H effective had all the contractions done. So any gauge stuff with the Hamiltonian is all, lots of different representations of Hamiltonian. They all become equivalent as long as they are correct for the Hamiltonian. So it was connected all the way through. The gauge matters for the wave function because that's what you have a little piece of.
Thank you for your talk. I just wanted to ask, you mentioned that that there's a situation where the entanglement propagates in this in the dynamics case, right? Could you point me to how folks tend to quantify that propagation? I guess you're using the von Neumann entropy to some degree, but.
So, Andrew, are you going to talk a little bit about entanglement growth in plate dynamics? Yes, I will. Okay, so I'm off the hook. I mean, I will show you, I will take that as an excuse to show my cool next plot, which, little advice, make cool plots, you'll be happy. Your advisor will be happy. Okay, so this shows the expectation value of S of Z when I hit it with S plus in the center. So before I do that, it's just flat, and then it looks like it's breaking sort of the speed of light because it's got correlations farther, but it's because it's a projective operator that just sort of picks out a piece of the wave function. So it's like, that's just showing the ground state correlations when I hit it with S plus. And then there's sort of a signal that spreads out like a light cone. Okay, and in that region, things are very complicated. So here's sort of measuring this correlation function, and things are very complicated in there. So you're not too surprised that it's got some more entanglement. going on in there. Yeah.
One quick question, like maybe I didn't get this detail, but in DMRG, during the sweeping, for the next step, let's say, do you start from the whole, let's say, sandwich and recontract it by fixing two different sites, or do you enlarge it, let's say, with an SVD and then recontract it on the other side?
So the typical way we do it is we have some initial wave function for all the tensors, maybe a product state. We then make the sandwiches on the right. We make every piece of the sandwich starting from the right, and we store that. So we make the first sandwich piece, and then the next edge tensor, and then the next one. We have a big array of them so that we don't have to recreate them when we're sweeping back. And we go all the way over to the first site, and we have a little H effective that we do, and then we start moving over, and we build up this vector of left edge tensors and work our way across. And as we go across, we're pulling something from memory, several minutes ago or something, that's like, oh, now I'm using this guy. And you sort of work your way across.
Okay, and another very quick question, like you were mentioning for some specific models, what's the dimension in 2D that we can consider? You mentioned Hubbard model. Do you have an estimate also for chemical models on?
Okay, so the chemical models, the way we usually think about it is how big an active space you can work with. Okay, and what the answer is depends on which group you ask and what their technology is. But the answers range from 50 to 100. Okay, so the issue with the chemical models is that you have the 4-index 2-electron interaction, which means a big Hamiltonian MPO. And and then there can also be entanglement that's pretty big in a molecule. There's a lot of interesting issues about that. That's something that I'm working a lot on. So my take on it is that there's a different form of basis that has a diagonal Hamiltonian. So it has instead of the C dagger, CC, it just has the diagonal form Ni and J, like it was a grid. But so I have this thing called Gausslets that tries to make the best basis of that type. And so that's an area that I'm working on. It simplifies the DMRG, but you need a bigger number of sites.
Okay, thank you very much.
Yeah.
Thanks. Maybe I just missed it. Like when you mentioned, like when you do this sweep, you want to first move the orthogonality center to
You can call it the OC if you want.
Okay, right, great. Like you want to move the OC to like the side wherever like the Hamiltonian is going to act on, and then you do this procedure. I guess, and you have some comment about how this really helps reduce the error. Like, is there a simple way to understand this? Like, should I expect it? I think I missed that point.
So if you, a lot of times we work with part of a system, and it's like, okay, I've got this qubit here. And of course, there's the rest of the universe, right? And so the sort of essential part for any sort of breakup of that system where you sort of want to ignore it is if you do put some pieces of it into the system, they have to be in an orthonormal basis, or nothing's going to work right. So it's basically that idea that the half of the MPS sticking out to the left from one, if you choose this orthonormality, that looks like the index there is indexing an orthonormal basis on the left. And so that's what makes everything work. And you do it on the other side. And if it's not an orthonormal basis, then when you sort of trace down what the SVD is doing, if it's an orthonormal basis, it's like the error in the truncation in the SVD is the same as the truncation of the wave function as a whole.
6. Oh my God.
Yeah, thanks. I just had 2 quick questions. Firstly, to do 2 time correlation functions, can I just evolve and then unevolve?
Oh, So the organization of that, I can't give you an immediate answer. There are tricks that you can do, and evolving back might, increase errors, and so I don't know the optimal choice. It's a question of just piecing together the pieces in the right way, and sometimes you don't want to do all the evolution that you need to, but you leave it for a final contraction or something. So there's some tricks there, and I can't tell you the answer off the top of my head.
Okay, interesting. And my second question was, yeah, you said like 2 dimensions is harder than 1 dimension because you have to do this cut, so you have more entanglement. Is 3 dimensions then also harder than 2?
Yes.
Okay. Thanks.
So in quantum chemistry, if what is the dimension of a molecule? Well, if you ask a condensed matter physicist, he might say 0. It's not infinite in any direction. And if you ask, a quantum chemist, he might say 3 dimensions. We only work in 3 dimensions. And it's all a question of whether you're trying to look inside the atoms and stuff, what the effective thing is. But there is a natural truncation that's not the area law of just, if you have a Hartree-Fock state and you cut it sharply, it's still only got a certain number of orbitals on each side. Okay, so it's like there's a different kind of truncation there that comes in, and so it's more complicated. In general, the sort of thinking about area laws is a little bit more complicated in this case where you're working with a basis.
Super cool. Thanks.
Yeah.
Hi, thanks for the great talk. And I just want to ask, so when you talk about the contraction, so you talk about there are different ways, and then some of them are more efficient than the others. So does that mean like no matter how you do the contraction, technically you always arrive at the same unique solution defined by your MPS configuration?
So if I do one of these time correlation things, there's a time here, and so there's an e to the minus IHT, ITH, somewhere in there. And so do you want to evolve the ground state, or do you want to evolve both sides of the operator? You have some choices there of just how you manipulate those things. So that's the easiest. And then suppose we put 2 different times here. We wanted both to be adjustable and some sort of non-trivial thing. Where you put the operators is a choice that you make and usually people experiment a little bit to see what works better in practice, just to minimize calculation time with a given error.
Okay, but once you fix your kind of tensor network graph, do you also have a fixed result?
So this was all about doing time evolution with a matrix product state. So of course you might not be doing something with a matrix product state. You might have reasons for doing something else. And you can also use the time as sort of one direction and write something with a tensor network that goes in space and time.
Okay.
So there's some fancy choices.
Okay, thank you. So then if we just focus on solving for the ground state, then I assume that doesn't matter.
Yeah, there's a choice. There's always, for a system that's not just a 1D chain, there's always the choice of the path through the system. And the key thing you want to think about is I want to minimize the entanglement of every cut as I go along the chain.
Okay. Thank you.
It's a neat cube.
It's very neat. I haven't had the chance to hold it yet, so it's very it's more squishy than you think it is. More of like an intuition question. I'm curious about your thoughts on how much further we have left to go, how much wiggle room we have with contraction schemes. For a general problem, yes, finding the optimal contraction path is NP hard, but there have been some recent randomized algorithms that seemingly do very well. So I was kind of curious about your thoughts about how much more room do we have until we literally have no other, maybe we've reached the total ceiling of how far we can classically take contraction?
Well, okay, so by contraction, you mean you're given a tensor network and you just want to contract it.
Yeah.
Not the finding the ground state or anything.
Yeah, that's to say, given any random network that can be written as a tensor network.
It's hard to predict these things. There's this technique that has recently been, well, it's been used for a few years, but I just recently noticed, called belief propagation, that has some new takes on it. Very interesting. So, you know, I would not try to say that we've done everything we can. There's tricks that we haven't thought of.
Okay, thank you.
Thank you. So yeah, I have two questions. The first one is about tree tensor networks on the chemistry applications. What is your opinion on that? Would tree tensor networks really fit into chemistry application?
Well, I've sometimes thought of them as a natural thing to do, not necessarily, even if you had a chain molecule or, you know, hydrogen chain or, you know, some chain of atoms, you know, you could think of a comb, which is a subset of trees, going down towards the nucleus. It's like, oh, you know, the area law, that sort of thing. It's like, that's sort of a space thing where we think about spins, but, you know, it's like you'd like to separate out the different energies. And so as you go towards the core, the shells, you'd like to separate those off. So you could think of a comb would be like, here's the molecule, and then I go down in this direction towards each nucleus. So that's a natural thing, but I've never seen that done. Okay, there's a cost for tree tensor networks in calculation time that you have to overcome, because you have an extra index, and so there's an immediate cost, and then you need a smaller bond dimension to result to make up for that. So I've you know, thought about these things a little bit, but haven't done anything, and so I think some other people have thought of sort of more general trees that they try to optimize that are not at all the way I was thinking of them. And so I don't have a strong opinion on those.
Okay, yeah, thanks. Then the second question is about the Gauss-let thing. So you mentioned that then the Hamiltonian term, instead of a C dagger, CC, you just have this number operator term.
Yeah, NI and J.
But then it would, of course, increase the number of tensors that you need, the size that you need to represent the whole system. Would it be a good trade-off, to have a simplified MPO, the Hamiltonian operator, but then you have to include way more sites, but because it also requires a lot of memory to store all of the sites?
That's what I'm trying to figure out. So it depends. So the question is the best sort of algorithm that takes advantage of the NI, NJ over a big space of possible ways you can do things. You know, is that got some advantages over the best traditional method? And so that's a lot of different things to try out, to think about. So I've been thinking about those. You know, it's a work in progress.
Okay.
So no clear answer yet.
Okay, thank you.
Thanks for the great lecture. I was wondering how the bond dimension required for a certain error scales as simulated time scale or coupling strength.
Let's see. Let's see. The first thing is that for some people and some level of rigor, you're not going to get a satisfactory answer from me. My style is to, you know, think about algorithms and you know, always look at what practically works for the system that we're interested in now. And so I tend to ignore the accurate error estimates. Not that they're not important, it's just like, okay, I focus on different things. But I make plots like this, and you know, this was a system where the beta onslots gave us an exact answer. And you can see how the accuracy, this is the error in the energy relative to the beta Onsot's exact solution for this system. And you can see how it's behaving, and once you're below the gap, it looks fairly exponential. But I haven't tried to quantify it. And so you can ask other people and probably get better answers.
Thank you so much.